Question number 14, which weak acid has a pKa of approximately 10? You can use the equation pKa equals negative log of Ka, and we have all the Ka values here for us. Also, the pKa is always approximately equal to the negative exponent, so that's another way to quickly solve this problem. Write a balanced equation to show the reaction between HCOOH, a weak acid, and OH minus, a strong base. Because we have a strong base, we're going to be using forward arrow reaction. We only use equilibrium arrows when both the acid and the base are weak. If one of them is strong, or if both of them are strong, we use forward arrow. Because HOOH is the acid, that means that it is going to lose H+. When you write its formula over on this side, you're going to get rid of one of the hydrogens. It doesn't matter which one. And you're also going to take its charge down. It's losing a positive charge, so you're going to go from neutral to negative. The base is going to gain that H+. So that means that you are going to go from 1 hydrogen to 2, and you're going to take its charge up from negative to neutral. That looks funny. H2O. There's the reaction. Question 16, 10 milliliters of 1 molar acid is titrated with 1 molar of hydroxide. How many milliliters of hydroxide are needed to reach this equivalence point? So for a titration problem, you're going to have an acid and you're going to have a base, and you've got a total of 4 pieces of information between the acid and the base. For the acid, you have a molarity. We know for this is our acid information. So the molarity is 1 molar, and also the volume, and we know the volume here is 10 milliliters. And for the base, same thing, 2 pieces of information. We know that our base is 1 molar. The volume is the unknown in this particular titration problem. How many milliliters do we need? For any titration problem, there's always going to be these 4 pieces of information, and any one of them could be your unknown, and you're trying to solve for it. You're going to set up your titration problem, start with the thing that you have all of the data for. We know all of the information about the acid. Use that data to convert into moles. So we know that our acid is 1 molar, which means that we have 1 mole HCOOH per liter. We also know that we have 0.01 liters of that acid, so that's going to be the first thing we do. Second thing that we do is go up to our balanced equation, which we have written out, and we're going to look at the mole to mole ratio of the acid and the base, and it's pretty much always 1-to-1. 1 mole of OH minus per 1 mole of HCOOH. And so this is going to tell us how many moles we need for the reaction. The last thing that we're going to do is use molarity as a conversion factor to go between moles and liters of that solution. The molarity is 1.0 per, so that means 1 mole per liter. Moles of OH cancel out, and we've got some pretty tricky math here. The ones cancel out. These ones cancel out. We are left with 0.010 liters, which is the same as 10 milliliters. And maybe if you're very clever, you may have seen that from the beginning and you never even needed to walk through the problem in the first place, and that's totally fine. So question 17, calculate the pH at the equivalence point for this titration in problems 15 and 16. Yuck. Okay, so for this problem, we are going to need to set up an ice table. So I'm peeking up at the balanced equation that I wrote in problem 15, because I'm going to need to copy that down here for my ice table. HCOOH plus OH minus, strong base, so forward reaction, HCOO minus, and H2O. So I just copied the balanced equation from problem 15. And now I'm going to make an ice table. Now remember, when you're making ice tables for titrations and also for buffers, these ice tables need to always be in moles because the volume is changing. So we need the initial number of moles of HCOOH. Well, we have the molarity of HCOOH, 1 mole per liter, and we have the volume, 0.010 liters. So that's how many moles we have initially. So we've got that part figured out. Now we need to figure out the moles of the OH minus. Well, this problem is telling us we're at the equivalence point, and at the equivalence point, the definition is that the moles of the acid are equal to the moles of the base. So if our initial moles of acid are 0.01, then that means that's how much base we have as well. We, like always with the ice tables, we don't have any products yet. Now, because this is a forward reaction ice table, we don't have X down here. We know exactly how much is going to react. We're going to take, of these two, our limiting reactant. Well, they are present in the exact same amount, so they're both the limiting reactant. And we're going to subtract that amount in our change and add that amount to the product side. And I don't know why I'm still paying attention to water here. So when this reaction is done, we have, all that we have is 0.01 moles. Don't forget, it's in moles, HCOO minus. We're trying to calculate the pH. So what we need to ask ourselves now is, how does this guy affect pH? How is this affecting the pH? Look at your list of acidic and basic cations and anions. This is an anion, and anions can either be neutral or basic. This is not on your list of neutral anions, so that means that this is a basic anion. This is a base, and that is how it affects the pH. It's a base. So the next thing that we have to do is write a reaction where this guy is acting like a base. So here comes another ice table and another reaction. HCOO minus with water, because this is not a strong acid and it's not a strong base, we have equilibrium, and the products are HCOOH and OH minus. It's just remaking the stuff that we started with. Ice table. This is not anymore. This is not a titration ice table. It's also not a buffer ice table, which means we want this ice table to be in molarity. It's not a titration. You might say, wait a minute, we're doing a titration problem. This is the ice table that's associated with the titration up here. The titration is over, it's done, and now we're trying to calculate the pH of the solution that's left over from the titration. So this ice table has nothing to do with titration anymore. So we need our initial amount of HCOO minus. Don't get excited. It's not 0.010. That is how many moles we have, and we want to convert back into molarity. So that's fine. You know how to do that. The moles, 0.010 moles, divided by the volume. Be careful because you mixed two solutions together. What were their volumes? We had, we can see from up here, we had 10 milliliters of the acid. So I'm going to add that down here, 0.01 liters. And what about our volume of OH minus? Well, thankfully, that's actually the answer to problem 16. We figured that out in problem 16. So we don't have to recalculate it. So that is the volume of this solution. And this is what we are using to calculate the molarity of our HCOO minus. 0.01 moles divided by 0.01 plus 0.01 liters, 0.5 molar. And in terms of HCOOH and OH minus, if we look back up at the ice table, we didn't end with any of those. So that means in our new ice table, we're starting with 0. This, because it is a weak base, we don't know how much of it is going to react. We only know that for the strong acids and the strong bases. We can assume, again, that X is very small. So here is our ice table. In molarities, our goal is to calculate the pH of the solution. We're going to have an easier time if we start by calculating the pOH of the solution, because X is the OH minus concentration, so we can use X to calculate pOH. In order to solve for X, we need to set up an equilibrium expression. This is going to be a Kb. Kb is going to be HCOOH times OH minus over HCOO minus. The problem gave us Ka. Of course, it gave us Ka. We can use Ka times Kb equals Kw to solve for Kb. Kw, which is 1 times 10 to the minus 14, divided by Ka, 1.7 times 10 to the minus 4. Kb is 5.88 times 10 to the minus 11, and that is equal to x squared over 0.5. Now let's solve for x. 5.88 times 10 to the minus 11 times 0.5, and take the square root. X is 5.4 times 10 to the minus 6. That's going to help us figure out pOH. Negative log of 5.4 times 10 to the minus 6 is 5.3. And last but not least, this marathon of a problem, pH plus pOH equals 14. So pH must be 8.7. There it is.